Alright, so first things first, Eagle Nebula, Pillars of Creation. Really cool image. I know I used it before, but why can't I use it again? It's a cool image. Anyway, so this video, as the title will be indicating, I haven't written the title yet, but Artificial Gravity. This is going to be a little bit of a weird video because it's one I kind of wish I were good at writing scripts for, because there's a number of topics I want to cover here, starting with some of the actual physics, some of the actual science involved with gravity, because I realized I was making certain mistakes that I can hand wave things away. I can do that with what I've already written in my science fiction, where it's like I've got enough pieces where it's like, oh yeah, the solution to this problem is like those things combined together. Now stop asking me questions. I can do that. But it is interesting because there's other examples of science fiction as I look at my movie and television collection where I'm not aware of them doing this stuff, which it's possible that they do. It's just you don't portray it in movies or television because, well, you kind of just need artificial gravity in those because the sets are built on Earth. You're kind of stuck with Earth's gravity. But yeah, anyway. So what is the actual physics with gravity? So the force of gravity is calculated as the gravitational constant times the mass of object 1 times the mass of object 2 divided by the square of the distance between them. Technically, it's the distance between their centers of gravity. And this is actually very relevant because technically, if you... Well, here, let's do it this way. So if you have an object here that has some mass to it, when you go into it, the mass below you is all that counts for calculating the force of gravity. The mass above you doesn't count. So technically, if you go 100 miles into the Earth, the mass above you does not contribute to the gravity you will feel. Okay? Now there's also, I want to point out, because it comes up a little bit later in this, we have inverse square law in the formula directly, okay? That is going to be very relevant because that's where I realized that, oh yeah, I'm doing something wrong. Well, I kind of can fix it, but it has to do with the inverse square law. But yeah, so force of gravity is that. And by the way, when I'm showing some graphs, which is why I'm over on this side of the video and we're going to have images up there, it says gravitational force. I'm just basically using one unit for the mass of object 2. Mass of object 1 is going to be primarily the Earth, but object 2 is just one unit, whatever it is, so it's force instead of acceleration, but it's the same numerical value either way. Okay, so as I said, in theory, you go 100 miles down, the mass above you doesn't count. Here's where it gets kind of interesting, that one. Because you might be thinking, oh, so if we go down in the Earth, then we get lighter. Actually, not for Earth. So this is my recreation of the preliminary reference Earth model. I've got the paper up, PREM, if you want to look it up. It's from 1980, but when I was looking stuff up about the density of the Earth at different depths, it seemed like this is it. We've not come up with better data than this. And it actually does include, I'm just scrolling down to actually find the page. Table 1, which is page 12, gives formulas. Yeah, actually gives formulas to calculate the density of the Earth at an arbitrary depth. It's really neat, and that's what I used to build up this graph. But as you can see, and this graph is for gravitational force, so I did to take care of its density. Okay, then what is the mass based on the volume? And I'm assuming that it is rotationally symmetrical, so it's not like, if I go in this direction, moving out from the core instead of that direction, I'm assuming it's all the same. There's a uniform density based on radius, I should say it that way. And also I should note, the units here are kilometers. On the next two graphs, they're meters. There's a reason for that, but for now, we're working with kilometers. But the thing that I got distracted, I want to point out, is if you look, there's actually a peak gravity that's about 10, or almost 11, for the gravitational force. But at the surface, we're used to 9.8. That peak is at, hopefully it's clear enough in this graph, that peak is at the edge of the Earth's core. Specifically, the outer core is the section labeled here. That's kind of wild, isn't it? So if you go down into the Earth, technically, it does look like the lower mantle. It curves back up a little bit at the end, but it still does seem like if you were to drill down into the Earth, even thousands of kilometers, you will find the force of gravity increasing on you because the core is that heavy and that dense. Putting it another way, the density of the mantle and of the crust and those like transition zone LVZ and LID, which I will grant I don't actually know what those are, what those stand for, but in any case, those are all so low density that the inverse square law is more powerful. Like, they're slowing the reduction of gravity due to distance, but they're not overcoming it. Now, it is also worth noting, it's over distance. So the fact we're already at, what is that? It's about 3,500 kilometers for the size of the core. And actually, because I have the thing open, yeah, the outer core in the paper goes to 3,480 kilometers. Okay, so the core is really big, but it's because it's the distance in the gravitational formula, it's the distance from the center of gravity. That distance is already so far out that the inverse square law, which, hang on, let me turn that off so you can see my hand. The inverse square law, it's an exponential curve there. At over 3,000 kilometers, almost 3,500, you're already at like a very flat portion. But it still is the reduction due to distance there is overcoming the additional mass of the mantle and so on. So yeah, kind of wild, right? And definitely not something I remember being taught before in high school or college. I mean, to be fair, the stuff I was studying would not bring this up. It just wouldn't be relevant. This would be relevant in certain classes, just not the ones I would have been taking. But yeah, so this is just covering the Earth. So from the center of the Earth all the way to the surface of the Earth. Now this graph is a little different. This I basically just extended out the distance to be about 90 meters above the surface. But it's starting 10 meters in, so we're actually looking at 100 meters from one side to the other. Okay? And the transition from ocean to space, and I think it is explained... No, it isn't. I'm not sure if it's like supposed... Well, it shouldn't be oceanic crust, because they actually do record it. Okay, yeah, so just looking at the table that I pulled the information out of, it's, like this is just with the ocean, they are accounting for the mass of water, okay? But for that to, the 6,371,000 mark, that's the surface of the Earth, so everything above that is space, as in we're now above the surface of the Earth. Look at how flat it is. Okay, we are so far away at that point from the center of the Earth, from the Earth's center of gravity, that inverse square law is almost flat. Not quite. But it is still really close. And this is not, like, even 90 meters above is barely lower force of gravity compared to where basically I am sitting right now. Okay? Now, this is very important because of what the next graph is, which the way I have it labeled is actually spaghettification, and there's a reason why it's that, but this is units in meters. And the idea here is, okay, let's say that we have a artificial gravity emitter here, and it is tuned so that, say, 1 centimeter out from it, okay, you have the force of gravity at the surface of the Earth. Now, I've adjusted the scale so we're concerned with the distance from that plate, because that's what you would actually be standing on. That's the floor plate. So the actual gravity below that floor plate and above the emitter is would be greater, but that's not where you're standing. But still, so if you're doing that, if you're standing there, you're going to have at the bottom of your feet 9.82 meters per second squared for the acceleration due to gravity, so multiply that by the relevant mass, and you get the force. Again, we're assuming that it's the It is 1 unit of mass, whatever that is, just 1 unit, so we get force. But at about 2 meters, yeah, we're at about 1. That's a big change, especially when you're somebody like me who I'm not 2 meters tall, but it doesn't take much rounding to get to 2 meters for me. So, yeah, and even at 1 meter, so the height of a child, you're still looking at what, about 2.5 for the force. That's a huge change. That really is. And why is that? It's because you are so near the source of gravity, the center of gravity. So now the inverse square law is very, very powerful, and that's why I have this labeled spaghettification in my thing. You're not seeing this. Like the file name for the graph is that. Because spaghettification is basically the same thing here, but instead of it being from like Earth's gravity at your feet to just almost no gravity at your head, it's the idea of tolerable gravity at your head and very intense gravity at your feet, such that you get... Actually, I got silly putty. That'll work. So you get pulled like that because the gravity at the base is so much greater than the gravity at your feet is so much greater than the gravity at your head. You get pulled, and even though you may have been kind of wide, because of the pulling, you get pulled thin. Spaghettification. Pulled into spaghetti. So it's kind of the same idea, except it shouldn't be fatal, as spaghettification is described as. It is also, I'm trying to remember where it was. I know that some places where they will mention that like larger black holes are actually safer in that regard than smaller ones. Because smaller ones you can get so much closer that you basically have this graph where there is such an intense change. Larger ones, it's more like this graph where, like in theory, if you could walk on the Schwarzschild radius, the actual edge of the black hole, if you could walk on a supermassive black hole, spaghettification wouldn't be an issue. But if you would walk on, say, a stellar mass black hole, it would be like this. So you would actually be spaghettified. And that would not be good. It would not be comfortable. All right, so what does this got to do with science fiction? Well, as I was saying for this graph, it's... Here's the plate you're walking on, here's the emitter. That's, you're going from Earth gravity at your feet to almost no gravity at your head. And for one deck, that's not going to be comfortable, and it's something that you would need to account for. I mean, it's also, imagine what happens if you trip. Which, yeah, because you'd likely still be pulled down because there's enough mass in your lower half that is being... That's where the greater gravitational force is. So if you were to trip, you'd fall down, but you'd very rapidly change the force of gravity on your head as you tip over. This would be not a good experience. Definitely not. But it's not a concern in basically any science fiction I can think of. And I've got my examples there. I've also got the examples that I've written. Now, the way I cheat, I'm pretty sure I did say that. I've recorded this video a few times, trying to get better each time. The way I can cheat is with 2 different things that I describe in the books, and one of them I've actually described in another video. In the warp field video, I talk about the idea of the intensity of the warp field, a discovery about something that was figured out how to be done with the warp fields, that's actually like as impressive or more impressive than constructing the warp field itself, was to have a near uniform intensity for it. So basically a square wave versus a normal round wave. And I know I talked about that in that video. But in theory, I could say, hey, they also did that for gravity. Because that way, the force at your feet is the same as the force at your head. So you don't have these issues. That's not unreasonable. And I'm comfortable with that being the hand-wavy solution. Another solution, though, is I describe, I think in both, I call my ship Catherine and a letter from Catherine. I think in both I do describe the idea that there are actually some emitters, and these would be the most advanced emitters, that instead of it being that here's where the force of gravity pulls you in, it can actually project the center of gravity, the center of attraction off of itself. and this is used. I know it's in a letter from Catherine because it's talked about for like maneuvering cargo onto a ship, uh, onto the exterior of a ship. So you'd need to be using gravity emitters, but that you actually have it projected out, so that way you don't immediately slam cargo into the side, which would be dangerous, but it also can, give some cushion, some distance there, so that as you move, because if they're not rigidly attached, as you accelerate, that there's going to be a little bit of time that they'll push in. So you want that little bit of a gap, that little cushion there. So in theory, with both of those, it would definitely be reasonable that you could have, over the course of your deck, the height of a deck, this, where it is basically flat. Yeah, and it is something that it's funny to me because, like, I got movies and television that there's stuff in there where they'd be using artificial gravity. And it's like, in some cases, they will even try to depict that something can fall from one deck to another, which doesn't necessarily make sense. Because if the gravity emitter is set up in each deck, then that means that the thing falling would go like this, because the gravity would pull it back up. Because this emitter would be more intense than the emitter down here for the next deck down. Unless, of course, it's falling really fast. The specific example I'm thinking of, though, and like I can see the movie right there, that wouldn't be the case, though, because it's like actually going through, it's eating through the deck, so it would not have sufficient momentum to launch itself. Okay, well then what's the alternative? You would need it to have like a single source of gravity all the way at the bottom of the ship that is going through the entire ship, so that way it would naturally pull from one deck to another, just like if you were to drop something from one floor to another in a house or other building. Yeah, then you run into this problem, though, all over again, because now it's just the bottom of the ship has very high gravity and the top of the ship has very low. I mean, to be fair, it's a movie. It's a television show. We kind of have our sets built on Earth, so we are kind of stuck with this gravity. It's just how it is. But it is just, I kind of enjoy the idea of stopping and considering, okay, how could this actually work? Because it is something that I try to do with my science fiction. Like, hopefully you can get the impression if you look at the presentation that I did, that I do try to have everything be reasonable, be explainable. And I realize that this is something that we just take for granted. That really we shouldn't. That the way it's showed in television and in movies is not sensible. It doesn't actually make sense. But it's necessary because we film on Earth. So it's like, it would be one of those things that now that I'm conscious of it, the next Catherine Rose story that's such science fiction, space-based science fiction, is actually going to be set on planets, so it won't be relevant there. But maybe in a later one, it's something I may, in fact, specifically write out, specifically address, because, like, yeah, I do need this solution, because it is a real problem. Like, if we were to develop the technology for artificial gravity, I could see somebody, well, hopefully they would think of it. If not, though, I could see somebody like, yeah, putting into a spaceship, putting that thing up there, and people getting awfully sick because their heads are so much lighter than their feet. Every time they trip and fall, they pass out because of the sudden change in force on their head. I mean, that would not be unreasonable to me, that it would actually knock you out, the sudden change, because that would affect your blood pressure and stuff. So, yeah, I mean, but chances are that kind of situation, no, they would just have figured out a solution. But they would be aware of it and have to figure out a solution, like making it as a giant ring, and in the center is where the actual emitter is, and you just are on the ring then and feeling it. But it would have to be really, really giant, because I mean, remember, to get this flat, we're talking about about 6 million meters. Yeah, that's very big. You wouldn't have to be that big, but still. I'm trying to remember, I don't remember the name of it. I know I've not seen it, but some movie where they try to depict that the way they produce artificial gravity is, and also in 2001, A Space Odyssey, they have it where you are, in that one, it is, the ship is a ring and it's spinning. So you've got centripetal force pushing you out, simulating gravity. But in this more recent movie, I think it is just Um, you have like a mass on this side. And the spacecraft's on this side, and it's just spinning like that. To produce the same effect. It's not a solid ring though. Yeah, it's like that. That can work, but it's so absolutely massive. I honestly would not be surprised if we were to develop artificial gravity, that we wouldn't that we actually wouldn't use it in these situations. That we'd use it in other ways, because that is just, you'd have to go to such massive sizes. Which technically at some point I do want to do a video on the design of spaceships, and once you can get away from material cost and you don't need to worry about entering atmospheres, you can make ships as big as you want. Space, because we have aerodynamics, but there's not like spaceodynamics. Not sure actually what the term would be for that. So it's like you could just go really large. You don't need a sleek design. You could go big. There can be other issues, but yeah. I'm just trying to remember. I feel like there was something else I wanted to mention, but it's escaped me, because that happens. But yeah, I mean, artificial gravity is just one of those funny things. As I said, legitimately for me, I remember what it is now. I want to mention. I kind of neglected that. Yeah, the practicality of it in a ship is a problem because of that. But at least I got enough pieces that it's not completely a hand wave and stop asking questions. It's more of a hand wave it. The answer's there. Now stop asking me questions. I do remember the thing that I wanted to also mention. I actually also use artificial gravity in the first book, in I Call My Ship Catherine. Which, yes, I know it's the one I don't recommend, but bear with me. It's actually an integral part of terraforming, in that the terraformer has these very powerful, I don't remember what I called them, but they are satellites that he puts in orbit around a planet, and full network around there. And they are able to produce very intense and focused gravitational fields. So he actually can change the surface of a planet by gravity. So he can basically just, I'll get the silly putty again. He can, just use gravity to pull something up and get a mountain range, or push it down to get a valley. He even is able to use it to... Nope, that did not work. I was hoping to get it to actually snap. Nope. There we go. To have it break apart and start moving tectonic plates to get that going. Because those are actually necessary for... tectonic plates, and the movement of them is actually necessary for the recycling of atmospheres. So you would need that if you wanted to take a planet that was dead, or seemingly dead, and make it livable, at least for long periods of time. So that you would need to do that. And I did kind of have an idea for the design of the visual design, but I mean that's not exactly relevant. But yeah, so it is. Artificial gravity would legitimately be one of the most impressive and most useful technologies to ever be invented, because there are so many things that the idea of just remotely and potentially very intensely applying a force, either pulling or pushing, is huge. Now I do want to be clear on one thing. I've been talking about artificial gravity. Anti-gravity would be something a little different, so that's where you're actually countering it. I'm not as sure about that, because gravity is one of those weird things in that it's all magnitude. There is nothing in existence we've observed that has negative, that has an ability to cancel out gravity. So I'm not sure how realistic anti-gravity is. One possibility is antimatter may possess anti-gravity, but we've only ever made it in small enough quantities that gravity isn't in play. So we don't know about that one. And just one thing, going back to the satellite thing, because you might be thinking, well, wait, how can you have such intense gravity being produced if this can be an issue? My answer to that would be that these satellites are basically designed to create gravity field lasers. Because lasers do get around the inverse square law because it's focused. It doesn't disperse out. It is focused and it's coherent in one direction. So would be able to do that, but it does have a lens system, so it can focus to be very large, focus to be very small, and it's so that is all actually handled in there. Yeah, I don't know if I will do. I haven't done anti-gravity in my stories, so I don't know if I will try to do a video on that. But it's also, I don't know what more I could really say. I mean, it's the idea that you can somehow counter gravity, but gravity is only an intensity. In nature, I'm pretty sure we've only ever seen it as an intensity, so I'm not sure how you could really counter it. Although now that I think there was something where in theory, it's been too long and it might have been like somebody just saying it, not an actual truth, that a current on a superconductor, I honestly don't remember this. You can look it up yourself. Like, if you get it going powerfully enough or fast enough, they would actually notice a reduction in gravity there. But I don't know if that is actually a reduction in gravity or if there's something else going on. That's why it's like it might have just been somebody saying that isn't necessarily accurate or is misinterpreted. Because also like magnetic locking with a superconductor, some people think that that's magnetic levitation. It's not. It's very different. And that's okay. So to try to very quickly explain that, since this video is already getting long, magnetic levitation would be when you have just two magnets like that oppose each other. So you bring them together and they push apart. That's levitation, and actually it's quantum locking, not magnetic locking, I think is the term. In that case, you actually have, it happens with superconductors because some superconductors have impurities in them, intentionally they go through them. Superconductor itself is not magnetic, but these impurities can be, and what can actually happen is the magnetic field of a normal magnet will enter into those impurities, pass through the superconductor, so it'll go through like that. But so many of the field lines go in there, and it's so strongly in there that it resists any movement through the field. So it's actually locked relative to the field. It's actually really, really neat. And in theory, you can then have a track where basically it has to stay on the same, the superconductor has to stay on the same field line. But if you have a track built that goes around, it'll just go around and around and around. Because it's just not interacting with the field. It's riding on it. It's really neat, but it is not levitation. It is a different effect. And yeah, I guess that's really all I wanted to point out was that is not levitation. It's really neat though. Look that up. Look that up though. It is neat to see. Especially because it is. You can then, and I've seen videos where people take that and then just grab the thing and they'll just turn it and release, and it's like it stays there because it's locked in position relative to the field. With levitation, it is just trying to find like a stable state. So it's like, okay, based on the mass, we're gonna be this far apart. Increase the mass that far apart, decrease it there. But this is like, no, it's like you put it there and it's locked. It's held there. It's really neat. Anyway, yeah, I should probably stop talking. But yeah, artificial gravity. It's just, as I already said, it legitimately would be one of the most significant, most impressive pieces of technology if ever actually invented. Because there's so many ways it could be used, even without anti-gravity. Even without that, there's so much you could use that for. I mean, you could use it to maneuver things. It would be better than Velcro, except Velcro is passive. This would technically be energy. It would be expending some sort of energy to create the field, but it's still, you could do so much. So much, because I guess another way to put it is, currently a lot of people, like in science fiction television movies, they magnetize themselves to stay attached to like the outer hull of a ship. Okay. You get this issue though, because it's the suit, potentially just the feet of the suit that are magnetized, so your head is still floating. That could be kind of weird. In theory, you could actually then be floating in the suit. It could be very awkward. Whereas gravity, if you're using that instead, now, especially if you do overcome this issue, in that case, it would be very even. It would be much more comfortable. So, yeah, artificial gravity is really neat. Okay, yeah, half an hour. More than enough of my talking. My apologies for that. I'll see you next time.